Let's talk about geometrical interpretation of the vector product. Just like for the scalar product, the vector product has a geometrical interpretation. We already seen one in the previous lecture, in 10.4. The one we saw was that if we take the vector product of two vectors which are linearly independent, the resulting vector is going to be perpendicular to the plane generated by the two vectors I'm multiplying. Now let's see a couple of more geometrical interpretations. And the first one is that the length, the norm of the vector product of v times w equals the norm of v times the norm of w times sine of theta. Now this formula is somehow similar to the one we have seen for the scalar product, where theta is the angle between v and w. Remember that for the scalar product we were already obtaining a number, whereas here v vector w is a vector. Therefore, typical mistake that the students do in trying to remembering this formula is just to take the vector product of v times w on the left and then stating that this vector product equals this product of three real numbers here on the right hand side. But the product of three real numbers is a number, is a scalar. Therefore, they obtain an equality between a vector and a scalar, which makes no sense. These are two different objects. This is a vector in R3, and this is a number in R. So the best way to remember it is to observe the relationship with the similar formula for the scalar product, where in that case, here on the left, we actually got a real number, and therefore we had an equality between two real numbers. So scalar product v times w equal the norm of v times the norm of w times the cosine of the angle between the two. In this case, the cosine becomes sine, and we cannot take the vector product of the two vectors, but we have to take the norm. Therefore, we have still a relationship between the angle of the two vectors and the norm of the vector product of v times w. The second important geometrical interpretation is the following. The norm of v vector w, so the same number as before in the previous formula, equals the area of the parallelogram with vertices, the origin, and then the two vectors, and then the sum of the two vectors. So we have here the origin of the coordinate system in R3, and then we have two vectors that we denote with the points as usual. So we have v here, w here, and then we have to consider the parallelogram generated by these 3 points, which means to complete it with v plus w and considering that parallelogram. So like this. The key remark is that equality 2 provides a way to compute the area of any triangular region as long as one of the vertices is 0, is the origin. And how do we do that? Let's start with the triangle, and let's take one of its vertices to be the origin. Then we can call the other two vertices, one the vector v and the other vector w. If we take the norm of the vector product of v times w, we get the area of this parallelogram, the region bounded by this parallelogram. okay, whose last vertex is v plus w. But obviously, the area of the triangular region bounded by this the initial triangle is just this area divided by 2. So area of the triangular region is just the norm of v vector w divided by 2. And this allows to compute the area of any flat region, let's say a region embedded in a plane in R3, and bounded by any polygon, because any polygonal region can be subdivided in triangular regions. And indeed, we don't even need that the whole region is contained in a plane, so it is flat. We just need that every triangle we are applying this formula to is flat. So we don't need this interior part to being embedded in some spherical surface or something which is not flat. For example, if we want to compute the surface area of a tetrahedron, each of the sides of a tetrahedron is flat, although they don't belong all to the same plane. Therefore, we can apply this formula to each of them and then sum all the area to compute the total area of the tetrahedron. Okay, so having a formula to compute the surface area of triangular regions makes this formula much more flexible than the one for the parallelogram. Okay, it can be applied to any piecewise flat triangular region, which enlarges very much the field of applications compared to taking just parallelogram regions.